don't know if you can have editions after 3 editions or something, but I guess you can. So this is I guess it's an emerging tradition that we're sort of also bringing, as well as having people that are sort of really experienced in deploying data science methods in Africa. Bringing in people who understand the state of the art, not necessarily in African domains. And I think one reason why we can do that very plausibly is because it's very easy to transfer the lessons applied at the cutting edge into problems in Africa if you understand the problems in Africa. So this is a fast route. It's not like these methods are disassociated. So I've moved to Amazon, I've been there for 10 months, and the commonality in the problem sets that we have in Amazon is really similar to the problems that you end up facing in Africa. So I'm really pleased to welcome Ralf Herbrich. So Ralf, I've known Ralf for 15 years. So we were postdocs at Microsoft Research together in Cambridge.
That was 18 years ago.
Was that 18 years?
18 years.
18 years ago. Yeah, depressing, wasn't it?
It is. It's why you have grey hair and I've lost hair.
I don't believe, you know, we met at kindergarten together. Ralf had more hair, I had less grey hair in those days. I've known Ralf ever since, and he's had an extraordinary career. We went different directions at that stage. I moved into academia, and Ralf was at Microsoft, I think, 12 years.
Yeah.
And did some amazing things around Microsoft games in the Xbox, player ranking matching, there we go. Yeah, I remember this. We moved from Microsoft Research to applications. He's been someone who started from a very theoretical. If you read his book, he's got a book on kernel machines. You'll see it's very, very theoretical. But he moved. He realized that the action was at the applications area, and he moved in Microsoft away from Microsoft Research into the application groups. And then he was a sort of founding member of the machine learning at Facebook. In fact, he recruited out the current head of applied machine learning, who's another friend, Wikikinero Candela. But then he was given this amazing opportunity, well, amazing for him, it sounds a super intimidating opportunity to me, to actually move to Berlin and build a brand new office for Amazon in a new city, doing a new thing for Amazon, which is machine learning across the company. An extraordinary challenge to do that, and he has carried out very successfully. So successfully, he made it so nice that I decided after 3 years of him sorting everything out, it was going to be comfortable enough for me to come in and do something in Cambridge. So he's been a great inspiration for me. But I think what I really love about this meeting, and I'm sure he'll say himself, he's been here, a day and a half, and he's already really inspired by the sort of things that are going on here. So I've already introduced him for too long, but he's going to tell you about machine learning and others.
Thank you. Thank you very much. Okay, I'll try to use the mic, but I tend to walk quite a bit. So we've got quite a lot of stuff to go through. Some hands-on. I gotta have some mathematics. As Neil said, I do like math. I think there is a strong connection between math and the application. But before I start, how many people know Amazon? It's very good. No, really? How many people know Amazon? It's only half the room. Very good, very good, very good. Now let me ask you that question. How many people know what's the mission of Amazon? What does Amazon strive to be? Sell books. Sell books, that's right. Actually, no, it's not right. Amazon mission isn't to sell books. Say again? Host databases. Not there yet. You can cheat. It's in the internet, by the way. Nope, this is for all of Amazon. What's the driving force at Amazon? What drives every single project that Amazon does? Okay? To make computation easily available. I think it's a good way of putting it. John? Making money. That's actually, it's interesting. That's quite explicitly not a stated goal. Let me read, yeah, okay. That's right, that's right. To be Earth's most customer-centric company in the world. So that is the mission. And whether you buy books, whether you are a developer, right? I think it's less about the revenue or the profit. We do capture profit later in the talk. Now, the reason I said that is the best way to understand Amazon and also why machine learning is so important is to look at the customers that Amazon serves. And I think we've mentioned 2 here. So Amazon's got about 294, I think it's in the 300 million now, active customers that buy, that go to Amazon.com or Amazon.de or Amazon.co.uk and buy. So they're on the buying side of a marketplace. But there's also, if you wanted to sell, you can become a seller. You have some artwork you do, or some jewelry, or some books yourself you write. You can become a seller. In fact, we have over 2 million sellers as customers. There's a lot of tools when you're selling, like making sure the customers are not fraudulent, the sellers are not fraudulent. FBA you see on here, fulfilled by Amazon. So if you're a seller, you have some goods, but you don't want to deal with the hassle of bringing it to the post and storing it in a storage. Amazon offers you that they fulfill it. So they basically store it for you. And then when a customer orders it, they're going to do all the shipping within a day, all the returns. Developers, that's a customer segment. That's people that want to run computation, that want to quickly move data from A to B. So that's a customer segment Amazon serves. And then authors and creators, so in the digital space. So if you write a book or you shoot a video or movie and you want to sell that or you want to watch it, again, that's a set of customers that we serve. And that's the best way to understand Amazon. Whenever you want to understand why is Amazon going into that space, is what's the customer pain point that Amazon's trying to solve. Now, when you come to the digital space, you obviously, this is no longer atoms, right? It's no longer moving things from A to B, like a book from the bookshelf to my bookshelf. This is actually moving bits, and bits have to have meaning. So in order to make sense of the meaning, you might need some hardware devices to see them. So if these are books, e-books, Amazon got itself into the business 10 years ago of those devices. Everyone knows what those devices are? It's the Kindle Paperwhite, the tablet, the Fire HD, the Fire series. That's when you want to consume ebooks. If you want to consume music, Amazon produced this device. Everyone knows what that is? This is the tube there on the left. Looks a bit like that. Speaks a bit human. It's called Alexa or Echo. The device is called Echo, and the service that speaks with you is a voice-controlled service. So you pretty much just speak, Alexa, can you play music from One Republic? And it just starts playing it. Or Alexa, what's the weather in Tanzania and Arusha today? And it just tells you. You can even control the lights and the heating with it. So that's a device that basically links the digital to the physical world. Here's a device that very few people know. You know what that device is? Anyone knows what that device is? It's a magic wand. No, it's actually called an Amazon Dash wand. And what it is it looks like a torch. It's that long. And it's for the convenience in the kitchen. So when you're in the kitchen and you run out of beans or you run out of apples or strawberries, typically it's not the best time to put your hands on a computer because it gets pretty dirty. So what it has is a button, you see that here, where you can speak into it and you can fill your card. It also has a barcode scanner. So if you just hold it on a barcode, it scans it, and it basically allows you to fill your shopping cart when you buy fresh products or what we call consumables in the kitchen. It's very robust. It can fall in the water. It's water resistant. It can fall on the floor. It's just there to increase the convenience that how do you shop online when your hands are dirty? Okay, and do you know that device? That's a games console. No, it's called a Fire TV and a games console. This is when you want to consume games, digital, like programs, binary software. And if you want to consume that one, well, you need some device on which to play them. And if you want to watch a movie, that's your device as well. In fact, it's now voice controlled in addition to having a remote control. Good. Now, why is machine learning so important? It's actually pretty simple to explain with what we call the virtuous cycle. So the virtuous cycle says customer experience in any form of retail is what Amazon wants to start to maximize. So what is driving a better customer experience when you go shopping? Whether you shop for compute, whether you shop for books, or whether you shop for music, music to play while you're on the road. What is typically a good thing? What do you think increases? So Amazon has a very simple belief, which is customers never said we want less choice. In fact, they've never said we want less choice and we want it with a higher inconvenience. People usually say having more choice and having more convenience in finding what I'm looking for and getting it quickly, whether it comes, something that comes within a day from me ordering it online, or even a half a day within the same day, that's a higher convenience. So the belief that Amazon has is that customers having more choice and having higher convenience in choosing and in delivering is usually improving customer experience. The same goes for compute. Like we have, and I'm going to show you that later, we have choices in the services that you want to do, not just pure compute. And even in pure compute, we have over 50 different instance types. Like you can have one with lots of memory, little memory, with GPUs, with 4 GPUs, with 8 GPUs, with 16. You can have some with massive amount of memory, like a terabyte of RAM. So lots of choice is usually a better thing. But you want to make it convenient to choose, and you see that as well. Now, if you have a good customer experience, that usually means people use your service. They run your app, or they go to your web page and they order compute, books, and so forth. So that means you're going to drive traffic on that page or on that app. And with more traffic, you become a more interesting marketplace for people to sell on that marketplace. Because every customer goes and buys the books or buys the music there, that's a good place to list my music as well, or my books that I write. So with more sellers, you basically increase selection. And so what you get is a cycle, a spiral that accelerates itself. And what that leads to is an increasing amount of digitized information about the customer transaction that you have. So growth of that cycle comes from it being a loop. So it keeps accelerating itself. Now with that, you're actually you should be able to lower the costs. So as far as storing stuff physically goes, if you have more information what people want, that should typically help you. And that closes the second loop, because customers nowhere, not just at Amazon, have never said, I'd like to pay more. Typically customers like to pay less. So Amazon's philosophy is, with lower costs, we should be able to lower the prices. And what really makes a good customer experience, I can choose more, it's cheaper, and it's actually very convenient to find it and to receive it. That is the blueprint of Amazon's business model. Now, why I'm telling you this, because we're in a science conference, not in a business, is because when you look at these arrows, you look at these red arrows, these are processes that get digitized, that's digital now. And all of these processes, the only way for them to scale is actually to have some automation, some prediction of what people would do in this job. So when Amazon started 25 years ago, there are literally people hired that are given a catalog of 1,000 products and told, this shoe, this book, this particular jacket, and they got told to make sure that to buy exactly the right amount. So when you store it, we never run out of stock, but we never overstock, or close as possible. You can do this for a few thousand products. In fact, if you go to a supermarket, you typically have, in the really big supermarkets, you have 2,000, 3,000, maybe 5,000 different products. But if you go on the web page of Amazon now, you have 20 million different products that need to be reordered every single day. No, there's not enough, people couldn't do it, they couldn't comprehend the information. So the only way to actually keep operating these flywheels is to automate some of those processes, to use machine learning for that. And that's because this is the blueprint of how Amazon does its business, whether in digital and compute or in physical retail or in fresh fruit. Because these arrows are red, because these arrows can only be really continue to operate when you automate. That's why machine learning is so important. Now, as I said, we're going to cover 3 things, or basically 2. And the first part, I want to do a bit of theory, and in the second part, applications. I'm going to show you some actual applications where we use machine learning. And the first one, I have 2 aspects, so I'm not going to run through the classical, what machine learning models, like linear models are like, but I want to touch upon 2 things that I find incredibly important. First one is probability. Why is everyone talking about probability? Why is machine learning so closely linked to the notion of probability? And John alluded to it, and other speakers use the notion of probability a lot, but why is that? And secondly, when you want to put machine learning in practice, so you go from the theory, there are some interesting things you have to think about with resource constraints. And so once I've done that, I want to cover forecasting. I think I hinted to that. A machine translation, a problem where I'm going to demonstrate how you can very simply train a model, train a system that translates from any language to any other language. And then a future application, or an application that was recently launched, using cameras. So If you think about probability, and as Neil was saying, I've been sort of started very theoretically and then went more into practice. But when I have to, I thought about how can you formalize what a machine learning algorithm does? If you had to write a single equation, what would that look like? And the closest one I came up with is this one. So let me walk you through it. What a machine learning system does, it takes two inputs. So one is your data. So all your observations, and we think of the table that John showed earlier. He had a table of the locations and the latitude, longitudes, and so forth. That's all because one row of that table we call data, feature vector, typically. So that's what we typically call X. And Y is the label. Like, is this, if this is like a transaction of a customer, does customer buy the product? Did he click on it? If this is a fresh, ripeness prediction, is this ripe product or is this a rotten product? If this is a health record, is this patient ill or is this patient sick? Okay, so you typically have a collection of this data, descriptions of each entity, and then the class. And then you have every algorithm, whether it's a neural network, it's a Gaussian process, it's a linear model, typically has a mathematical model of mapping the inputs, the features that you can observe, that you can record with the sensors, to an output. But because it's in the future, there's typically a probability involved, an uncertainty. How likely is it that a customer is actually going to buy? How likely is it that the patient is sick? How likely is it that this road can be traveled? And all these models are parameterized by W. So you take these mathematical models, they're implicitly or explicitly encoded. In neural networks, this is a layered network. In Gaussian processes, that's typically a covariance function. You take your data, and then a machine learning algorithm maps this to a function, and that function takes any input and makes a prediction with uncertainty. If you have no labels on the data, it's a similar one. I'm not going to go through that. Now, in here, I used the notion of probability. So why did I use the notion of probability? And the reason I used it is threefold. So the first one is it's the mathematics of uncertainty. So about 1944, a guy called Cox thought about the following problem. It's actually really interesting when you read that publication because he talks about a robot that has intelligence. So this was before computers were invented. And he said, if we have to design this robot to behave rationally, like we do, make rational decisions, the robot has to assign some plausibility to anything that it says. If the robot says, it's going to rain, it should attach a plausibility. What's the minimum set of assumptions we can make, or what's a reasonable set of assumptions we can make on plausibility? And the first assumption that Cox made is, he said, plausibility should be a number, a real number. Okay, so that's pretty, I find that a very weak assumption. So plausibility isn't some grade, it's like 1 star, 2 star, 3 star. No, he said any plausibility measure that a machine that we build could use should be a real number. Minus infinite, minus 10,000, plus 10,000, but a real number. The second one he said is that regardless of how we ask the question, whether we say it's going to rain tomorrow, or we're going to say it's not going to not rain tomorrow, that should not change the plausibility. If I'm asking the question in a different way, logically the same thing, it cannot change the plausibility. Okay? Again, I find this quite an easy one. And the third one, it's a little longer, but let me explain it. He said it has to be monotonous. So what that means is, he said, if I have any reasonable plausibility, and the plausibility of a statement A increases strictly over when I know C prime. So for example, it's rained yesterday, so now the plausibility of rain, if that's A, is more likely than it didn't rain yesterday, which was C. Okay, so if C prime is it rained yesterday, and C is it didn't rain yesterday, then if the plausibility of rain today increases, and the plausibility of some other statement, like it's going to rain in Berlin, is completely unaffected whether or not it rained here. So if the plausibility of a statement A increases strictly when you know more information and leaves another statement completely unaffected, then it must be that the plausibility cannot go down when I look at both these things, when I look at rain in Arusha and rain in Berlin. Because one of them got more likely, the other one was unaffected, so both of them cannot get less likely. So he said that's a reasonable assumption that any rational argument, any machine that we build that reasons about the future should have. And when you make these three assumptions, it's a number, it's independent how you ask the questions, and it's monotonous. It means that plausibility doesn't go down if I get more information. Then he could prove that the only mathematical calculus, the only mathematics that guarantee that this is fulfilled is probability theory as you learn it in school. So that's why I believe so strongly in probability as a measure for uncertainty, because in machine learning we predict the future. What we do is when we use it in search, we're predicting the next 10 seconds. You type a letter, and in the next 10 seconds you choose some of the suggestions that you're getting. When we're predicting demand for fashion, we predict 18 months in the future. Obviously there is uncertainty. But I think the only calculus, if you believe in 1, 2, and 3 here, you have to use probability. There's no other mathematical model you can use. And now you might say, I don't believe it should be a real number. I think plausibility should be a number of stars. Then you get a different calculus. But if that's the minimum thing you assume, that's why probability is such an essential concept. That's why, since the last 10 years, I strongly believe whenever the notion of we build a system, predicts the future comes up, it has to be a probability. And we have to use the calculus. The second one is a practical one. I'm a trained computer scientist. So I studied computer science, that's why I still like doing that. And there's something really nice about probabilistic models that allow it to map computation from like the model itself, the P of X given, sort of Y given X, to computation and storage. And that's the way I think about computers. They have memory, they have a CPU, and there's a bus that connects the two. Why is that? So there's a model of a probability called a vector graph. So it's very simple to explain. It's literally a picture. So when you have variables that you model, so the variables could be your data or something that generates your data. So this could be locations and whether or not a patient was sick or whether or not a customer bought. A vector graph simply says that any black square is a vector, it's mathematically a function, and it's connected to some variables, and only the variables it's connected to are variables that are occurring in the function. So my probability is a product of lots of functions, so it's a product of the black squares, and the black squares are not all using all variables. So it basically means there's some locality. Some factors only use A, some factors only use B, some factors use A, B, and C. Okay, so it's just saying how does my probability, if I look at it as a product of functions, how does it decompose? And that's useful because if I look at one of the most classical models, I have n data points. I want to predict whether or not a patient is sick or whether or not a click happened. I have a bunch of parameters and the model is uncertain about the parameters. I can represent it this way. There's an uncertainty about the parameters, and then for every data point, I have a data model, a mathematical model of the data. In fact, if I assume that all my parameters are factorizing, I get this graph, and not every data point uses every parameter. And now, the nice thing is that all the squares you can show are just computations. So every square corresponds to a computation that you have to perform on a chip. And all the round things are either data or parameters of the model that you need to estimate through the computation, what we call machine learning. So what you can do now is you can look at a model that's really large. So when I worked at Facebook, we looked at models that had literally 100 billion of these down here. And that would not fit in a computer. But this model really showed, well, you just group them up. And you know, all these ones are on one computer, all these ones are on one computer. And that's effectively what's known as MapReduce. Like you have your storage of the data here, and the communication across them happens through the variables that are linked. And then the same goes for variables. Like when the models we worked on at Facebook back 5 years ago, they had up to 10 billion parameters because we had a parameter per customer, and they have 1 billion customers. So if you have a parameter per Facebook user, you already have 1 billion parameters. Again, that doesn't fit in normal memory. So these graphical models allow you to chunk up that computation also. And so now you chunk up your parameter storage, and that's what, when you look at the literature, is known as a parameter server. And these edges between them, they're basically showing what communication has to happen. Either the communication is on the chip or the communication is across the network. But the nice thing is all this communication, storage and computation was all coming from the mathematical model. Like the mathematical model prescribed how you actually have the machines communicate with each other. And there's a nice one, if you go into MXNet, so this isn't just theoretical, I think I have that open here. So MXNet is something you can use when you install it in Python. You can actually try some of these algorithms out. I'm going to send this around later, where you can build these factor graphs. So you can say, I have a very simple factor graph that basically says x times y equals a number. I don't know what x and y is, but I know what the number is. So I'm declaring this graph, so x and y. I say it's a linear output with a squared loss, so I have a squared loss to the target variable, and the target variable I set at 1, and I initialize x and y at around 0 with a small uniform variation. Okay, so what are the plausible values for x and y if the product is 9? What are the most likely values that an algorithm should infer if two numbers multiplied give 9? It should give 3 and minus 3, right? And so if you look at the convergence of this algorithm, so what you see here is x and y. And of course we wanted 9, so 9 is around here. Okay, that's the loss you get from it. So here you have nearly a loss of 0. So you can see the algorithm as it performs it effectively walks this line, and in the code you simply have a way to solve this. So you have these messages are called forwards and backward messages. So what the arrows were are now expressed. Oh, sorry, you couldn't see that. How do I do that? If I close that one? Okay. Now you can see it. Oh, sorry. I was showing it this. So here you define the variables in x and y, and then you define that the product is 9. And then you have forward, backward. So if you remember my picture had these black lines between the variables and the data. So the data is now 9. The variables is x and y. And you literally, this is literally saying forward along this arrow, backward along this arrow. And then if you run this, you get, this is a very simple one, you basically get the most likely solution at +3 and +3. And if you initialized here, you'd be -3, -3. That's the only possible solutions you get. The reason I'm using this simple example is what you see here is at the core of every recommender system. Because every recommender system is basically saying there is some effect strength by the customer, being me, and the product being a black jacket. And if those two, for me to like a black jacket, it means that I have to have parameters fitted so that my parameters times the parameters, we call them traits, parameters for the black jacket are giving a high value because I bought it, or giving a negative value because I didn't buy it. So what a recommender system solves is exactly that equation. You know that I bought the jacket, so you know that the product of my x and the jacket's y is high, but you need to know what was my vector in that space, what was the jacket's vector. So this isn't just a toy example, this is literally what happens with many variables in any recommender system. Good. Enough of that, so let's skip that one. Let's talk about the second aspect. So if probability is so important, what is the other thing that you need to consider when you put models, when you want to put models in production? And one of the things that was surprising to me is working at Microsoft, working at Facebook, or working at Amazon, working with anything that you put in practice is sometimes you use extremely simple models. So, we all know about neural networks with many layers and how accurate they are for example, for tasks where you translate from A to B, or where you make a prediction of is that image containing a face, and what's the expression on the face. But then when you look at tasks that are executed a lot, like ranking advertisements on Facebook, or ranking news stories, you see simpler models being used, and you see people talking about simpler models. And I always wondered why that is. And actually what it comes down to is when you want to deploy algorithms at large scale, the cost of compute starts to play a role, right? And let me give you an example. So first of all, what's the cost? What's a simple economic model? I think John said earlier, it's about profit. So profit is formally the money you take in minus the money that goes out, revenue minus cost. And I don't think I'm telling you a surprise that any in the long run, businesses do have to generate a non-negative profit or they're not sustainable. Now, let's look at a few numbers. They're a little old, but you can all get them from, they're all public numbers. Let's look at Facebook's revenue 2 years ago. So Facebook has a revenue of 17.9 billion per year. Okay, so it's a big number, it's a huge amount of money. So 17.9 billion is about 49 million in a single day if Facebook were to earn that money through advertising every single day. Okay? Now, advertising is computational. All advertising there is not like a human decide. You come to Facebook's page and then it's decided what ad to show. This is an algorithm that runs. That algorithm was trained on some data and it predicts the probability that the customer is going to click, on that ad. So how many of those predictions need to be done? Well, let's look at that. Let's actually see. We have statistics of 2015 is Facebook had about 1 billion daily active user. So I think it's 1.3 now, something like that, 1.3, right? So 1 billion users active every single day. And also, let's forget about the ads. They don't come, no one comes, I mean, very few people come for ads to Facebook. Most people come to connect with their friends. And they connect with their friends to the stories they see. But the stories they see is a subset of every single thing that all the friends on Facebook do. So there's an algorithm that has to rank all the stories, all the check-ins, all the photos, all the status updates that all your friends have been done since the last time you were there. And again, there is a number, again, it's public number, it's about 1,500. So for every single user per day, Facebook has to algorithmically rank 1,500 stories in that day, minimum, at least. So that means if you look at how many predictions of how likely is the user, how likely is the user going to click, like, share that story, it's 1.5 times 10 to the 12. It's a pretty big number. It's basically 1,500 billion predictions that have to be done. And now let's assume that we don't want to show ads. Let's just see how much money could we spend for that. Remember, we make 50 million per day. We do 1,500 billion computations by ML models that predict. So if I divide these two numbers, if I basically take $50 million and divide it by 1,500 billion predictions, I'm arriving at $3 microdollars. So $3 microdollars is the absolute maximum money of compute, storage, and communication that can be spent. In fact, that would mean we can show ads. So we probably only spend $1 microdollar. And that would still be a little high because I think there's other activities that Facebook does. So it's below $1 microdollar of computation that can be spent for every single one of those story rankings. And that's a very small amount of storage that you can, and compute you can actually perform. And now take into account that one GPU box is roughly the energy consumption of 20 CPU boxes. You have to spend a lot of money just cooling this computation. So if you were to shift this all to GPUs, you need much more energy efficient GPUs in order to perform these highly accurate, but highly energy constraining resource computations. And it's something really not to forget. I mean, right now we're seeing initially when you start your model, your algorithms usually run on a few hundred instances, but if they take on, if the global community uses Facebook or search, or if we have, every farmer has an IoT sensor, and we're going to analyze that in real time, that is so much information that the cost of compute will actually play a major role when you want to put this in production. And I think from all I can see, the amount of automated predictions is only going to go up from here, not down. So this is, over time, this is going to become more and more a consideration that has to be taken into account. So with that, let's move on to 3 applications. So the first one, before I talk about the first one, let me give a bit of an overview. Where are we doing machine learning? As Neil was saying, we have a team in Berlin, but that's really not the only team. We have a team in Seattle. We do have quite a few teams in Europe. So the Berlin machine learning team, and we have a team in Bangalore. And these were sort of the 3 teams that have been around the longest. But we also have a team in Cambridge now, and a team in Los Angeles. Team in Los Angeles is a lot focused on machine translation. Cambridge team very, very active on data science. We do have machine learning also in teams specifically for products. So you saw some products before, like Alexa. And we talked about search. So there's a team, for example, in Boston that's very active on the application area of ML to speech recognition. The application, or you see the one A9, the application area of ML to ranking products in search. So as you can see, it's a lot around the globe. It's not everywhere. I'm sure we should fill the whole globe. We shouldn't just fill Europe, North America, and India. But typically our approach is we're going to go where the experts are. That's why you have so many hubs and so many locations. And if you had to estimate in how many systems at Amazon is machine learning already used, what's some numbers? 10 systems? 50? 100? 200? All? Not all, I wish all, but about 200 to 300 systems. So you see some here. There's some obvious ones. I think everyone knows product recommendation. People who bought that also bought that. It's probably the earliest application. But then there is some not so obvious one, like review analysis. Every single time a customer posts a review. About 5 years ago, we ran out of capacity to have people look at that. And the reason it's looked at that is for customer experience. If you want to buy a product, you want to make sure that the review talks about the product. It doesn't talk about shipping. It doesn't use foul language. Whether it's positive or negative doesn't matter, but it should talk about the product. It should tell you something about that stereo or that book or that jacket you want to buy. The speech recognition in Alexa is fully trained, it's fully learned from a machine learning model. Even the answers it gives, the knowledge that it extracts in order to give answers, get partially extracted by matching language. But one big problem you see here is demand forecasting. It's probably the most impactful usage of ML at Amazon. And so what's the problem? The problem is that, in particular one that we worked on, you see for 3 years here, when you have a fashion product, like a jacket or a shoe or jeans, you need, this is because of the industry, you need to predict up to 18 months in the future. So how many units, how many jackets will actually be sold in France or in all of America or in all of Europe or in all of Mexico or in all of Brazil or in all of India? And that's a very long time. And in that fashion industry, it's only in the fashion industry such a long time. And one of the challenges is that it's sort of a time series forecasting problems, but you have the size variation. So if you sell books, or if you buy books, you already have a sort of a heavy skew. Because the business model says we want to have the largest selection, you end up having a huge tail of products that sell less than 1 unit a week, less than 1 unit a month even, okay, one piece. But for fashion, you have an extra order of magnitude less data per product. And the reason is that when Amazon buys the shoe, it has to decide in which sizes. It has to decide in size 7, size 8, size 9, 10, 11, 12. But when you buy a shoe, you don't choose the size. You have a certain foot, and either the shoe fits in there or not. You can't just say, I'm going to buy a size 12 shoe if you have a size 8 foot. So the buyer doesn't pick the size, but the buyer, but the seller, the Amazon has to buy from the retailer. They actually have to pick the size. And there's about 8.5 sizes on average. So everything you have about particular customers is now going to reduce by an order of magnitude because the sizes, or you have to at least model the size distribution explicitly. And so in pictures, and this is already some fashion product that sells a lot, the task you have to do with the machine is, and that's what people used to do manually, you look at that red line, assume this is now, so no one knows the future. It's called a back test. So the way we test this is that we show the past and predict the future. So you have the red line, so that's the number of individual jackets, let's say, that were sold, and you see this is December, this is December. So you see certain seasonality, right, from the training data. And the task is you have to go a year or up to 18 months in the future and say, where's the red line going to be? And the systems that we have, they don't do the red line prediction, because if you go 18 months in the future, there's no way you can get the number right. So what we do is we actually predict a very optimistic estimate, the 90% quantile. So basically, what number of units do we believe with 90% probability, and the 10% quantile, the P01 quantile. So it's like the distribution, when you think of it as a distribution, we take certain quantiles of that and we predict them. And here you can see again, the production systems, all the software is using probability as a first principle. So the green line is the optimistic, The purple line is the pessimistic. The peaks are easy because there's Christmas, there's seasonality, you can get that. But those non-peaks are very hard to get. And so you kind of have missing data, you need extra information about it. So what we, and the other thing we need to do is we actually need to model the individual number of units per every single day for 365 days in the future. So what we end up doing is using what's known as an empirical sample distribution. So if you wanted to represent that Gaussian processes use Gaussians, but Gaussians are real numbers, you can't buy 1.7 of a jacket. You can either buy a jacket or you can't buy a jacket. You can't, you know, you have to be integers that you use. And also, there isn't really a parameterized distribution for a 365-dimensional distribution in the future. So what we do is the simplest thing. The training data is literally the count of how many units per day were sold. That comes the input to a training procedure, and the output is a possible future. Think of it as the system imagines the exact trace of what happens in the next 365 days. Okay, but that's just one sample. So we actually generate 100 samples. So what we do is we generate another sample. And if the future is certain, we're going to end up with 100 vectors of integers that have 365 numbers in them. Each of them corresponding to how many units tomorrow, the day after tomorrow, the day after tomorrow, and so forth, all the way to a year from now. So that's the representation that we're choosing. So all that we need to do is, when we come back to the original one, we just have to decide, oops, what's our probability of the number of units for a given day in the future going to look like? And so we looked at that data, and to give you a sense of the size of that data, it's about 5 million, this is for one single marketplace, 5 million products, we have to do that. We have about an average 3 years of history for that, so that ends up being 4.5 billion individual counts that we train from. And the interesting one is some people call it Project Zero because 98% of this data is zero. It's the count zero. So if you were trying to fit any classical model like a negative binomial or Poisson, any textbook, you open a textbook and it says what models do you have for count data, it says Poisson. Yeah, the Poisson doesn't have that much probability mass at zero. So what we end up doing is one of the simplest models you can think of, which is we explicitly have a classification model that says is this particular day particular day t for product I, is this 0 on that day or is it 1? So we have a probabilistic model for that. In fact, is it 0 or bigger than 0? If it's bigger than 0, we have a model, is it 1 or is it bigger than 1? And if it's bigger than 1, we looked at the statistics, we use a Poisson, a classical count regression function. So if you were to put this to these graphical models, what we end up doing is for every single day, we have a description of the features. So this could include the price on that day, the promotions on that day. Is this day Thanksgiving? Is it Prime Day? Is this Valentine's? So this is all information that we encode here. This is basically each X is a row of the table that you saw in John's talk. And then the last column is how many units that we sell on that day. How many were sold in Germany on that day of this particular product. And since we have 3 different processes, one process which is this one, is it 1 or not? Is it 0 or not? Is it 1 or higher? Or is it 2? For every single one of the days, we have a variable that represents the parameters, the strength of how likely is it 0, how likely is it 1, and what's the rate of count above 1. Now, of course, one thing we don't have is it's a time series. So the demand of yesterday should have an influence on the demand of tomorrow. Typically, these things are not raggedy curves. They're somewhat smooth with some spikes in there. So what we also do is we also model a time evolution of what we call a latent variable from one day to the next. So what you end up doing is building this network. So this network is built in Spark. So Spark is one of the frameworks in which you can do stateful computations. And it's probably one of the largest Spark jobs in the world. But it ends up being, when you look at them again as the products, what's known as a Kalman filter. So that's the latent state, that's your likelihood model, and that's the data feature vector that you take. And to give you an example what it does in practice, so if this is a prediction of a demand to do from the past, If you ignore the time series component, so you just treat it as a classification problem, you're going to get predictions like this. And the blue line is the reality. Now what you see here is it gets far too certain because there's no uncertainty increase over time. There was no time evolution model, and obviously if you don't have it in the model, the predictions are not going to show it. If you use the classical Poisson, you see that we have the time evolution, meaning with time the uncertainty, this is the 90% quanta, as the 10%, keeps increasing, but this is now not taking into account the zeros. Just saying, this is a textbook model. This is what you find any textbook on time series. This is what you find any textbook on machine learning for classification. So you need to combine those two, and if you combine those two, which is what that model I just showed us, we've done is you get the time evolution piece, but with much less uncertainty over time. Another advantage is that often we are out of stock. So what that means is customer goes, he sees the genes, but the page says we no longer have anything in stock. So if we take that day, on that day, of course we cannot sell anything. So we have 0 number of units sold. But that's not the demand. The demand was higher. So if we don't take this into account, so basically we just assume that people from here to September didn't buy any, then the prediction in the futures are going to have a bias to 0 because we have a lot more zeros than there were actually zeros. But the real curve might have been a little higher here, but we couldn't observe it because we had nothing stored. So this is, again, the classical, if you take classical ML and treat them, the missing data, not as missing data, but as data that was 0 because you didn't observe it, you get what's known as a bias. So you get a prediction that is smaller because you have more zeros than you actually observed. Because it's a model where we have explicitly the variables for demand over time, we can, I'm not going into details, but you can average them out. You can, what's known as marginalization, and what you get is you get more uncertain where you didn't have demand. Demand might have been higher here, and then in the predictions the bias is removed, so you're more likely to be calibrated. But the other thing is, of course, you're more uncertain. You were lacking data here, so in the future you're going to have a higher uncertainty than here, but you cover the true demand, which is the black curve, rather than being constantly too small. When you now imagine at the scale at which Amazon runs, and this happens in 12 different marketplaces every single day for 5 million products, it's not something a person could even technically do. And a bias here means that you continue to be out of stock. And a small uncertainty here means that you're not having too much in the fulfillment centers. So the next one application that we did from 2013 to 15 is product machine translation, or product description machine translation. And the motivation for it is when we looked at, in 2013, when we looked at this map, we kind of knew that with trucks and with trains, we were able to quickly deliver something from that part to that part of the world. But there was something, when you look at Europe, that was different between the US and Europe. It wasn't the distance. So the distance from Poland to Spain is as small as the distance from the West Coast to the East Coast. But the West Coast people and the East Coast people in the US, they both speak English. But most Polish people don't speak Spanish, and most Spanish people don't speak Polish. So what we saw is that in Europe, and I think in many parts of the world, we have a separation of markets because of language. So they exist physically, they are close, but the people don't understand each other. So what we're doing is we run an experiment. So we took a few 10,000 product descriptions, and we had people translate them. And the way we chose them is that we looked at the lifetime profit. Again, same equation. Profit is revenue minus cost. By translating, you incur a cost. So you want to make sure that the cost is only incurred for products where you have that money left on the table. So we did translate. We asked people that typically translate books to translate products. And we did that from German to English. And we've listed them in, we listed those 30,000 products in the UK marketplace. So people that were in the UK all of a sudden saw products like this. Okay, so they saw this thing. Now this wasn't there. So it reads very much like a Selecta wooden toy. So that's a wooden toy, but it's actually from a German seller. You can see there's a translation mistake here that's happening. And not surprisingly, what that does is effectively increasing the selection. And our belief is more selection is higher customer experience. That happened. People actually bought that. We're looking for that. And so what we needed to do is we needed to bring the cost down. So we're looking into maybe we can sacrifice some quality. Maybe we can do this with a machine, with an algorithm. And so we then started working on models that are specifically tuned to translating the title and specifically tuned to translating the bullet points. If you look at this product again, there's some bullet points. These are typically not always full sentences. And these are not sentences at all. In fact, they contain sometimes brand names and size names. And then the product description is more like classical text for machine translation. So we built models for title, for bullet points, and for product description separately. Because it turns out if you take the classical machine translation model that you find on like Google Translate or Bing Translate or you name it, they're not tuned towards that type of data. And I see Mustafa nodding. I think it's very, if you wanted to use them to translate what Facebook users post, they wouldn't work very well compared to models where you actually translate what Facebook users post. And so worked on this for quite a few years. Don't want to go too much in detail, but I want to show you something because we released some of that about 4 weeks ago, a system called SOCI. So it's a sequence-to-sequence neural machine translation package. So it's basically a package where you have a time series model. That's one best way to think about it, is from token to token. So in this way, the token is the word, from word to word, from the source language to the target language. It supports both CPU and GPU encoding and decoding. And I thought, if Neil hasn't run off with his phone, I should actually be able to show you how to do that. Let me see. That's probably crashed, is it? Oh no, it's still there. So what you do is, it's called SOCI. So you go on AWS Lab SOCI on GitHub. You can clone that repository. And so the first thing that, as a user of it, if you wanted to use these models that we're using, is you get yourself an AWS Deep Learning Amazon Machine instance. So how does that work? Well, you type AWS Deep Learning AMI, and then you get this page, AWS Deep Learning AMI on Google. So if you go all the way down, oops, you say get started with AWS Deep Learning AMI. So you click on that. Oops, it's always risky. Is that working? You should be able to get that, but that's not there. Uh-oh. We'll see. So you get to this page. And on this page, you can basically choose. What you choose is here, coming back to the original point, more selection. You now have all the images that help you, images for a virtual machine that you get, that allow you to train, to just get the standard deep learning packages installed. So this one is, SOCI is built on MXNet. So if you use the Deep Learning AMI Ubuntu version, you should get to this page. And this page allows you to choose an instance type. So if we were to do this, we go on here. And you just choose the region. So in my case, I chose the Ireland region, continued. I should say I did this morning in the car. So this is really working really fast. I did the manual launch. Okay. So I wanted to launch it in Ireland. So what you end up with is so console looks like this. And I'm not going to go through next. So you can now choose the instance type. And you see here I have two. This is a for free instance. It's not very big. It's got one CPU. This one got a K80 GPU. So that's fairly powerful. It's about 5,000 cores, hardware threads. GPU and within, I think it was, we left Atomic and we arrived at Atomic, and in between I had the P2 instance running. So it's just loading. Yeah, it's just coming up. So all you do here is that instance. So it's running. So now you connect to it through a virtual instance. So right now just to give you a sense, I am connected. Well, you SSH into it. So I have two terminals running that are SSH'd into this instance. Okay, and the nice thing is if you look at that instance, can you see that? Can everyone see that? Good. If you look at that instance, you can see that things like Theano, so that's a neural network package, Keras, TensorFlow, MXNet, they're all pre-installed on that machine. And that machine also has a, oops, that's the wrong one. As I said, it has a NVIDIA P80. So right now it's running idle. So can everyone see that? I don't know. Right now it's 27 degrees, runs on 30 watts. And the instance, this is the GPU instance. The fan is not active because it's idle. Okay. So all you need to do is you need to download the data set. So there's a blog post. So for example, here's a publicly available data set from German and English. So I'm getting the first million examples of that one. So that one downloads done. So that's about, how big is that? 140 megabytes. I don't know if you can see that. So I just downloaded a German data set. Okay. Just to give you a sense how that looks. So it has every sentence from the European Commission. Let me see if I can make it a bit bigger. Oops. I can read that. European Commission, upcoming events, die Nachricht, die Anmeldung zur Veranstaltung kann vorgenommen werden. Okay, good. So now we need an English one. So there's a corresponding, this is a publicly available data set from the European Parliament. So I'm now getting the English data set, and that should be done. So let's look at that. So that has European Commission, upcoming events, the news, registration for the event can be submitted. That's literally a translation, line by line. First line, source language, second line. Each line have to be source target. Okay. We need some validation sets. So this is used in the training to make sure that you're not overfitting. So when you come to use a model, you typically want to make sure that you minimize the training error while looking, at the, while looking at some holdout data to make sure you're optimizing, you're making sure you're not overfitting on that training data. And then all you need to do is, this machine already has Python 3 installed in all the packages. You just do a Python, run the package sockItrain, source, send host language is train.de. So this was 1 million lines of the German data that we just downloaded. Target was the English. You have the validation set. Output the model. So when we do that, it finds the GPU. So you can see acquire GPU device, and now it uses MXNet. It uses basically what was known as an RNN model, a sequence-to-sequence model. And you can do this with any text. So the reason I'm demonstrating you this is that it literally takes you 5 to 6 minutes to run that. So if we do that, I think it'd be quite interesting because I talked about energy before. So let's watch our GPU. What happens with that one? It should be warming up. Okay, it's still cold. Let's look at the other one. This basically just, you can see what it did is it created the tokens. So it went through all the text, and every single word became a token. It tries to now take the sequence of words and predict what the German words are to the English words. So it created those 1 million sentences. They're loaded now. And if we watch this a bit, is it going up? 28, that's good. There's no process running yet. I think that's natural fluctuation. Now there's a process running. You see that? Python 3. So now we're filling a fair amount of memory on that GPU. 10 gig, I think. No, that's the bus. That's the amount of data we're pushing onto the GPU. Now the GPU does get a bit hotter. So now it's at 42 degrees. And now you can see the energy consumption. It just went up 4 times. And it keeps going at that energy consumption continuously. So this model is quite big. I can't wait. This takes about 2 hours to train. But it gives you a sense. When I talked about energy earlier, I said, for training, that's probably okay. But if you ran this one for prediction, first of all, it's expensive. But the energy consumption is pretty massive that it puts through. Okay? It's actually an interesting stat to look how hot the GPU is going to get. It's not going to go above 100. It's not going to melt. Okay, good. Let's come to the last one. Is that on? Yeah, I'm gonna distribute. I'm gonna give the instruction if you want to try this out yourself after the talk. Last one, visual systems. That's a fun one. So we start in 2014. So in 2014, a colleague from the Amazon Fresh team. People know what Amazon Fresh is? So it's Whole Foods. That's a good way of putting it. Since 10 years, Amazon has been looking at, like, when you think about what do people spend the money that they earn for? Okay, so some of it for rent, I think. What's the next biggest item that you have to pay for every single month after rent? Food, right? Food, that's right. And food has one of the problems that, in contrast to books, in contrast to shoes, in contrast to a toaster, a blender, food perishes. Food goes bad really quick, actually. So you need a quality control in there. And the colleague came up and said, you know, Ralf, what the state of the art in quality control in fresh fruit is? I said, no. He said, let me show you. And so I don't know if you can see the video. So what happens is, and this is industry practice. So when a farmer or a co-op delivers their fresh food to a retailer, to Amazon or other retailers, a sample is taken, a 1% sample of every fruit, and a person is doing the quality control. So what you see here is he's taking the strawberry, one clamshell, and empties it on a table and classifies it in 4 different grades. And then only grade A is the best grade. I think this is typically, now you have to throw it away. I think it's not good. First of all, you lose 1%. And if there is for every fruit, there is a percentage. If the amount of bad fruit is below that percentage, above that percentage, the trade is not going to happen. But also when you sell fresh fruit online, when you sell strawberries or apples or oranges or bananas, the difference between a supermarket and an online retailer is that in a supermarket you put it on a display, and you go to the supermarket, then you, as the customer, are making the final quality control. Because you go up and you grab the clamshell and you look at it and you go, yep, it's all very fresh, I'll take it. But when you order online, someone else has to do that. And the state of the art is manual labor today. That's the state of the art of this process. And it's actually not very accurate. So what's your estimate of how much food goes to waste between being harvested and arriving in your kitchen, in anyone's kitchen? Of course there's waste, right? Something's going to rot away. What percentage of fresh food is rotting away? 30%? 80%? Okay. 60%? It's about 50%. 50% of all fruit goes to waste. So what that means is, if you could improve the quality of that, first of all, you could lower the prices and the farmers would still make the same profit. Basically, every fruit is at least paid twice, because you have to pay for all the rotten food. Someone has to pay for the rotten food either. And for me, it hurts me deeply when food goes to waste. And half the fruit that gets harvested goes to waste, just because we're not very good at it, at judging the quality along the process. To me, is a call for action. And so the person said in 2014, do you think we can, I gave a high-level overview of what machine learning is. Do you think we can do something with algorithms that have sensors? And why don't we point a camera at this? And maybe we can do at least as good as people. And we tried at least as good as experts. And we've tried many, many things. So what you see here is an early prototype where we had we solved the haptics by having a person having blue gloves and just holding it on a camera, standard RGB camera. And then learning to classify each frame, whether or not this is a good strawberry, whether or not it's a good strawberry. So you see the predictions in real time here of good, okay, up to decayed. And whenever it's red, it means that the algorithm made a mistake because that frame was classified as not good, even though that was a good strawberry. Okay, so in this case was a good example. And it was interesting because one thing we found is that algorithms that operate on images, there's 2 things we found. The first one is you don't have a lot of training data. So you try to run your bespoken neural network model when you have a handful of labeled example. is not going to do so good, because there is no big collections of cats and dogs. No, there's no big collections of images of strawberries from a given camera system. The second thing, so it kind of really puts in perspective a range where models, highly nonlinear models like neural networks work and can't really work. The second thing we found is when you show an expert the video, the expert is only as good as the algorithm. But the accuracy of predicting the ripeness for the expert is way higher when they can use all their senses, when they can touch it and they can smell it and not just see it. So if they, there's definitely more senses that we are using as humans than just looking at a fruit. And so, the challenges for the machine is that the illumination matters, the occlusion matters, the viewpoint matters. Fruits come at different scale. I think bananas can be that big or that large. Strawberries can be that tiny. It's a good strawberry, or it can be really big. In fact, there's a funny story to share. And they have very natural variability within the range of fruits. So what we've done is we've looked at alternative imaging systems, not just RGB, but also we wanted to actually not just replicate the task that people do, which is to judge that something is good or bad, but what we wanted to do is, really interested to do is to do what is necessary to do when you want to store them and not have them rot, which is you need to be able to look at an image of a fruit and then predict at which point, how many hours from now, how many days from now, is it going to go bad? So how quickly do we have to sell it? Do we have to sell it locally, or can we still ship it to some other supermarket? And so what you see here is a data collection task that went on for over 4 weeks. So back in 2015, what we've done is we had some of our data scientists go out and buy 56 strawberries, and we bought Petri dishes, and we had this special camera system, and then every 6 hours we took the same strawberry and we kept taking pictures of it. So what you see here is the training set of 28. It was 52, it's 26. So you see 26 strawberries and 26 rows. So each of these little pictures is a strawberry, and age means we let it age. The room was pretty warm, it's 20 to 25 degrees, so there was not a fridge, so they would definitely go bad. And you can see it, I don't think you can recognize the strawberry, but when you recognize the picture, the color, you can get a sense. This is 2 weeks. So some we could simply not put on the Petri dish anymore because they were completely rotten. So this is where you see some gaps here. Also, 6 hours means that sometimes you had to go up in the middle of the night. So you have here you have a data set that has 600 or so observations, high definition images from a fruit in spectra that the human eye can't perceive, because we have to make up for smelling, and we have to make up. They don't taste them, but we have to make up for all the other senses, touching and 360 view that people have. And the model we wanted to learn is, can we, with this as input, all the spectras, can we predict the x-axis? Can we predict the age? Can we say at which age, and this is sort of normalized, so typically starting from here, you would not sell those anymore because they're getting too bad, okay? And what you see here is basically the test set where we used it and we predicted the age for every single image of all the strawberries that we took, that we held out. This is the other 26. From predicted freshest, top left, to predicted oldest or most advanced strawberry. And you can see it's a pretty good alignment, so it goes this way. And in fact, we've done measurements, and the accuracy that this model has in terms of predicting when it goes bad is above what humans can do. So, humans can probably say reasonably accurately, is it still okay? But you can't really predict, is it 2 more days, 3 more days, 3.5, 7 days. So that's I think it's pretty powerful. And it's something that we're currently in the phase of testing out in real production. So in one of our fulfillment centers in the US, we do have this system with this camera system in place, and we are collecting. We have now thousands of scans, obviously, because it's in productions, and we now have enough training data that we could think about more complex algorithms than when you have 26 or 52 examples to train from. So with that, I want to conclude, and really just sort of conclude with 3 messages. I think the first one is, what's machine learning? The best and simplest way for me to explain what it is, it's a translation task. It translates data from the past into hopefully accurate predictions in the future. Now, whether you do this with neural networks, you do this with Gaussian processes, with simple regression, with ordinal regression, that's just sort of a question how much data you have, how much computation you can use at prediction time. But at the core and at the essence is data. If you don't have data from the past, there is no need and no possibility to do machine learning. The second one I want to say is when you do want to use in practice, probability and finite resource constraints. I think I talked about energy. There is another one that I hadn't touched, which is time of prediction. Those really start to matter. They start to matter more than accuracy. And I have this belief, I discussed this also with Neil, is I think as we go forward, because ML or these predictive models become more and more present in our daily lives. You know, they go on our watches, they go on our heart bands. I think it's more important that we measure accuracy per amount of energy spent, per joule spent on predictions, rather than just accuracy. Right now we're in an obsession with accuracy only. And in practice it hurts us, and particularly when you want to roll it out on mobile devices or at scale for very large collections. And then last one is I think I hopefully convinced you that any type of machine learning we do, we're trying to do to improve customer experience. Lower prices, increase selection, or make it more convenient. Thank you. You have questions? Yeah.
You talked about problem sharing circuit I example.
Mm-hmm. Still running, isn't it? Oh yeah.
Who don't have a subscription?
For what?
Who don't have a subscription to AWS?
Yeah. No, let me show you this. I hear you. So, so if you have an AWS account, so meaning if you have an Amazon account, so you have a credit card linked to your electronic account, you can just go and there's tiers that are for free. So this is a tier called T2 Micro. So that processor would take a lot longer if you ran it. Typical compute is in the dollars per hour. So the one I showed you, right? I think I showed you P2 large. So you see that one, P2X large. That one, if you rent it by the day. So that's roughly $23 per day if you run it. But that's a very powerful computer. But typically, you rent it by the hour, not by the day. But you know what I will do after this talk, I'll shut this instance down, and then it probably cost me $6 right now. So if you have a credit card linked to an Amazon account, you can use that. I mean, I could demonstrate that with your account here. I don't need my account for this. There's nothing special. I used this is not my corporate account. This is my personal account. So does it answer your question? Anyone in the room should be replicating what I've just done. Although I would recommend probably you don't go for the P2X large instance. You can go for the C4 instance, pretty powerful, and it costs a little less. Your training time increases because SOC-I has two modes. I don't know if I demonstrated that, but you have a CPU mode, so you can run it and it trains with the CPUs only, or the GPU mode. So if you do the CPU one, all the instance types you see here, let's say, so you want to have C4 is the one I'd recommend, C4 large. That one has multi-core processor. The multi-cores will be used, but you're not using this energy-hungry GPU. Also, we do have grants. AWS has sort of educational grants, if you like, for teaching a class or so. So you can definitely apply for them, and that's typically for educational purposes. You get then a token. So you take your account, you link the token, and that just adds an amount of dollars you can spend for compute or for storage. Yeah, I wanted to show this one actually because we talked about selection and choice. So this is all I've shown you here is, so what you see here is if you type aws.amazon.com. Oh, sorry. Sorry. Am I in the PowerPoint? Whoa. Should be able to see now. Sorry. So what I was showing is, it's actually quite good because I have the billing information up. There's tiers here. So this is the screen that I flicked over. So when I chose the deep learning AMI, you have to choose which instance type you want to use. So the one that is for free is called a T2 Micro, but it's just got 1 gig of RAM. But you can use this for free for as long as you want. What I'd recommend if you want to have sort of a cost-efficient one is the C4 large instance. So that's 8 gig of RAM and 4 processors, 4 virtual CPUs that you're getting. The one I was demonstrating it on is a GPU compute instance, so that's this one. So that one has 4 cores on CPU and then a 5,000 core GPU, the Tesla GPU. So that's the one that's currently running. So if you look in here, I also have a T2 Micro instance running, and I have the whole task that I showed you. I've tested it last night on the T2 Micro instance. And anyone in the room should be able to use that if you have an AWS account. I mean, if you have an Amazon account, which is your AWS account. And what I was showing you earlier with the tokens, sorry, you can see this one. So that's just one of the services. So you saw the compute services, EC2, that's the one I showed on the screen. But you know, if you go down to AI, there's a bunch of other services to play with, and they're all the same thing, they're all charged against this account. So we haven't talked about them, but I showed you the instance type, but there's also one specifically for learning these sparse models we had earlier. That's not for the machine translation models. But you should try it out. Really, no kidding. I was in the car this morning, and then by the time I arrived here, the instance was spun up. And actually, just to show you how easily you spin it down. So this one is now, I'm going to kill that one because I really want to spend any more. So you go actions, and then you go, oops. Terminate. Maybe while the next question comes, you can see how this is terminated. And yes, terminate. So this one is now not costing me. The charge is by the hour. So it's in a minute it's done. It's terminated. But the P2 is still running. So the other instance is still there. So this one is still running at 73 degrees centigrade at full power. Still training. Yeah. Yes. Am I? Some results. Yeah, I think a good one that there's some books, but I think if you want to have a paper where a vector graph is put to good use and explained, there is a paper on TrueSkill. So if you type TrueSkill, like TrueSkill, that's a paper where we use it for ranking gamers. So one of the projects that I worked on almost 10 years ago is when you want to match people online. So people play, in these days my kids play Clash of Clans and everything all the time. But back in the day, you had to have an Xbox to play easily online. I think now, oops, it's pretty much every mobile does it. And one of the hard tasks there is which person of all the 100 or of all the thousands of people that are online, which 2 people are the ones that are most similar in skills. So if they both say I want to play online, they should get and battle it out on Clash of Clans, or battle it out on Halo, or battle it out on a virtual racing track. And so the system there is called TrueSkill, and it basically has this latent variable skill and the observed variable match outcome. And so this paper describes this pretty well. Yes. So when you compare 2 objects, so there is a notion of probability that I would apply in this case. So if you have, let's say I show you these 2 things, okay? And I ask this room, am I holding the same things in my left and right hand? Then, it's about 150 people in the room. And, I would think 140 of them say these are 2 different things. And 10 people in the back might say these are the same things. So the probability that these two things are the same. Is 10, is 140 over 150, that's the notional probability. There's still uncertainty in making the prediction if two items are the same or not. Because people would disagree. The same way that when we do the freshness prediction, we had an interesting experiment we've done. Because we were wondering what are the advantages and how reliable are people on this. So we took a toad, so a box, and put cucumbers and apples, and I think we didn't put strawberries in there, peppers. And we had several of them, and we gave them to a quality expert. So that's the job is called produce quality expert. So that's the job if you're doing what the man did there. And then we had about 10 of them. So we gave them a round, and then a half hour later we gave them the same box, but they didn't know. Okay? And the funny thing is that 20% of the predictions were different. So now to your notion of probability relevant, absolutely, because there's the probability is actually accurate. The best is actually more in the range of 80%. 20% is going to vary anyway. If you ask the same person the same question shortly after, they're going to change their opinion. So that's the notion of probability. That's what's called frequentist probability, what I'm describing to you. No, sorry, I misunderstood your question. That's a very good question, because I was stretching the truth a tiny bit. So I said there were three things that basically lead to probability. The number has to be a real number, plausibility. It has to be, irrespective of how you phrase the logical question, and it has to be monotonous. And then I said probability theory comes out. That's not true. What really comes out is a calculus that's equivalent to probability theory up to scaling. So anything, you could scale the probabilities, you could take the exponential of them. You'd get a calculus now where products become sums. But the rules of probability, base rule, would still look the same up to the scaling of the probabilities. So the scale 0, 1 is not coming out of the three axioms. It's arbitrary. So someone then shows, well, if they're all the same rules, what is a canonical scale we can choose? And then Cox said, why don't we choose 0 to 1? And any other scale, 0 to 500, minus 50 to plus 50, can be mapped back, and the same rules apply. You can even use nonlinear monotonous transformations, and you still get the same calculus. So, good question, yeah. 0, 1 does not come out. That's artificial. There's a question there. Jesus Christ. Finish.
Yes, thank you. I'm really interested in machine learning, but I got a challenge here. Is there any machine learning algorithm that can translate from word to word based on language dictionary? When you take when you think of the issue of semantics of a sentence.
Yep.
Take an example, somebody develops an application and it allows different people to comment. Then, what if that comment has to be read with someone who doesn't understand the language? Can it be able to translate it?
Can you translate comments? Is that the question?
Comment written in a certain language that any other user doesn't understand it.
So there's no training data. You have.
I mean, you have an application. Take an example of Facebook.
Yeah.
And somebody in China doesn't understand English, but you just commented something there in English, and the other user in China has to read or understand it. So how does it translate, maybe based on the language dictionary?
So the way, roughly speaking, the way it works is it learns, so there's these models called phrase-based translations. Language is quite structured. So, the grammar, it has a grammatical element, but what happens is that certain words tend to co-occur a lot. Like when I say, there's many words for walking in German. But depending on what object I mean, or in English you can say to go by bus or to go by plane. Both of them are sort of the notion of moving. and go bus, go plane co-occur, in German these are two different words. Okay? So what the model really learns is the co-occurrence of words in the source language. Let's say we take English to German, go walk, or go fly, or go by bus, or go by plane, and the equivalent word co-occurring in the other language. So if there is sufficient amount of training data where the algorithm can pick up these co-occurrence patterns, yes, it can learn that. It can learn the translation. I think other people would say the semantics is defined by the co-occurrence of particular, I call them tokens, but think of them as words. The co-occurrence of words in languages across two languages. So you have co-occurrence in source and co-occurrence in target language. What that model really learns is the co-occurrence patterns. What the neural network model can learn is co-occurrence patterns that have a longer chain. So some grammars like German have the verbs come all the way at the end of the sentence. And then you need a long chain to correlate them because they're not next to each other. And that's what these models use. They basically use the grammar and the co-occurrence of words to define meaning. The way they learn semantics, or the way they represent semantics, is the co-occurrence of words. And with neural networks, you can go over longer distances rather than over just next to each other. But there's no magic. Like I think I forgot the phrase, but there's a word for this representational semantics that it actually does. But it does heavily rely on the amount of training data. If a certain translation and training set only occurs once, it's typically too few times to generalize and learn the grammar. The same way that if you teach a young child to speak and they only heard a phrase once, they typically don't remember it and can't put it in context. So I noticed from my children, they grew up in Britain, we were German parents, and it took them a long while, like they were 9 years old and 6 years old when we moved back to Germany. It took them a long while to understand the meaning of the proverbs. So we have proverbs that make no sense if you translate them. I'm sure in every language they exist. And you could see that it wasn't just once or twice. It was literally tens to hundreds of times we had to explain to them that raining cats and dogs does not mean that cats and dogs fall from the sky, right? but because the semantics is something establishes itself also with people, I think, with recurrence of patterns. And does that answer your question? Thank you.
Hi. So I have a couple of questions with regards to the forecasting part of the talk.
Yeah.
You mentioned that you guys use Spark. Do you
Yes.
find that MLlib handles time series data well?
I think what we find is, so we don't use MLlib. We've extended MLlib.
Okay.
We found that the data processing, so getting the axis on my graph, on my picture, to be processed information from the raw input, that's where Spark really shines. It's really efficient there. But we also found that the stateful computation, so when you had to do the message passing, that was something that Spark wasn't really designed for. And we're actually looking now in other frameworks that are more efficient in terms of the communication, because all the communication is still via a bus. Like that's still, the state is stored in memory, but it's still distributed over a network bus. So it's much higher latency than if you have it on a single core. So we're now looking into for the pure learning part, the message passing part you saw, into alternatives. So we do the feature the data processing to the feature level in Spark, but then the learning outside of Spark.
So the other frameworks you're looking at, are they open source?
So again?
The other frameworks you're looking at?
It's the execution engine in MXNet. So MXNet has an execution engine also. So that one.
Okay. Then also you mentioned that you sort of decay your time series into a classification problem.
Mm-hmm.
Is that because deploying simple models to production is cheaper, or do you find that performance is better?
So in this one we don't have that much of a real-time constraint, and the volume is not that big. So it's 4.5 billion examples to train from, but we only do it once per day. We have hours of latency because it corresponds to physically people ordering. So the computational constraints are a little less there, and accuracy is more important. Because I think the best way to look at them is the Facebook example or the product search. These are micro decisions. So each decision of which news story to share on a Facebook feed is a decision that also generates tiny amounts of revenue and time. And so in micro decisions, energy starts to matter more. Deciding to buy 100 of these jackets is a macro decision. That's thousands of dollars that you have to commit as a result of that automated decision. And you're only going to commit that once a day, probably once a week. So the energy doesn't matter that much. The reason we decided, I'll tell you what, the reason we decided to use these time series is because we needed calibrated probabilities. Because of the scale of the decision you're taking, you really don't want to, like if you make a mistake there, you might be sitting on a huge pile of inventory that's worth millions of dollars. Just think about the fact that for all the products that are sold by Amazon, they had to be bought first. So now you look at the, if you now look at the statement, the balance sheet of Amazon at the end of the year, you divide by 365, you get a sense of the scale of financial decisions that these forecasting systems are doing. Mistakes really matter a lot financially. It's easy to make $1 million mistake there. It's really easy.
Then also, I'm curious, do you use any LSTM? Because they're supposed to be really good with...
We do, yeah, we do. In fact, in the, I believe in SOC-I we have LSTMs, but yeah, we are using LSTMs quite heavily.
Okay.
They refer to the long-range connections that I was just referring the previous person. In language you have these long-range connections for certain grammars, so that's where LSTMs really shine.
Then finally, is it possible for you to decompose how you separate your time series data? Because I assume you have a lot. So is it per product, per vendor, per market? Can you talk a bit about that?
Yeah, it's per market. I think that's the easiest to say. So each market has its own model running, and then we run for all products on that market.
Okay. If I have one vendor who maybe makes a sale today and then another sale next week, do you think it's possible for me to look at their particular traffic and be able to tell something meaningful about them? Or is that just too big data?
I think you're missing you may be able to do that, but then you want to generalize across vendors because the products, some products are often offered by more than one vendor. And the pattern is the buyer has not always just a brand preference. So I think it's very hard for people to accumulate that much pattern. You can look at one vendor's sales data, but not across all vendors for all types of similar products. I do see Shira sort of waving at me. I think I have to really, and I've went about an hour over, so I probably have to close here. Okay. Thank you. There was a person behind you that had a question, I think. They're there. That's right. You're getting the mic.
Thank you. My question goes to AWS S3 for storage. For IoT application, I want to deploy an IoT application on S3.
Yeah.
AWS S3. What is the procedure? Why do you need a device from you? Because most of the website company, the program there, device is to make sure when you're using the server, you have to use their device. Is it possible I can have my device and connect to your storage service and then be able to create the API and communicate everywhere?
This is not my area of expertise. This is much more for like Damon and John, but I think it is. We have Greengrass, which is our service here. So if you look at I have personally not used it. I was planning to do this later today. But we have our IoT platform where you can connect the devices, right?
Just come to the tutorial session after this on IoT. We're going to be covering exactly that.
Okay, great. Tutorial after this session is covering exactly that. That's a better answer than I can give. You had a question.
Yes, a quick one on machine translation. You mentioned that most of your features, well, you use Messico to train grammar parsing?
Not in Sockeye, no. So you can actually, if it's still running, and I didn't get disconnected. Let me see. So you can see, can you see that screen? Yeah, good. So, you know, if we look at that data, so you see what it's doing is, it basically creates a vocabulary. And it literally just uses a sequence-to-sequence model. It assigns an ID to each of them. Oops. So it literally just extracted all the words in Unicode, and it learns the token sequence of 145036, followed by 15303, followed by 19354. There's no extra information. In fact, they could mean anything. It doesn't really attach, it doesn't go on letter level.
No pre-processing.
The pre-processing is to split it at the spaces and remove the tabs. That's the pre-processing. Good. Shall we have some food, or is that food, or what is this? Yeah, let's have some food. I'm hungry.